Robotics preliminary design. The team is going to now speak about the Hexapod, so the second element of the combined design of the Scorpion. So I let Evan Klein introduce the team and start the presentation. Thank you for coming.
Welcome everyone. Going around the room, there's a green folder that's labeled specifications and requirements. There's a one-page sheet in there that has all the specifications and requirements for our project. We refer to that throughout our presentation, so it might be helpful as reference. Let's just give the projector a minute here to turn on. Over here on the side, I have the PreSept team with me, and today we're going to present our PreSept project as far as it relates to the preliminary design. My name is Evan Klein. I'm a mechanical engineering student here in Embry-Riddle, and I'm the design team lead for this project. Today we're going to go through the team that we've assembled, the problem statement that we were given, the problem solution that we came up with, the requirements and specifications we came up with to define our solution, as well as the design process we used, and then the mechanical, electrical, and software design that we generated from that path. Next, we're going to look at the unmet requirements that we are not meeting so far. We'll have some time for summary, acknowledgments, and we'll have about 15 minutes for questions at the end. So up here today, once again, my name is Evan Klein. Over here we have Mariah Sampson, David Olson, Magnus Bergman, Stephen Rudrich. Running the computer, we have Kevin Horn. Over here we have Sarah Pearson, Davis Fisher, Trenton Post, and Kristen Sander. Next, we're going to look at the organization chart for this team. Like I said, I'm the design team lead for this project. Sarah Pearson is my assistant design team lead, and then the rest of the group is split up into 3 sub-teams, electrical, mechanical, and software. For mechanical, we have Mariah Sampson as the lead. For electrical, we have David Olson, and for software, we have Magnus Berger. Now to look at the problem statement we were given for this project. We were given a task to design and fabricate a multi-purpose Hexapod autonomous robot platform with a flexible scorpion-like manipulator. The team that presented last was the scorpion-like manipulator. We are the Hexapod portion of this project. So us specifically, the PreSept team, we were given a goal to design a Hexapod to beat the 2017 RoboGames challenge. And there's more info on that online. We have another slide about that as well. I'd like to take this moment to thank some of the sponsors for our project. The College of Engineering and the Undergraduate Research Institute were instrumental in helping us with this project. To look at the RoboGames. The RoboGames is a 1 meter wide by 3 meter long arena that has some, they call it garbage, but they have obstacles distributed throughout the course, and you need to design a 4- or 6-legged robot in order to navigate that course and get to the other side in the shortest time possible. Now we're going to look at the requirements that we came up with for this project. This again references the sheet that you might all have in front of you and the folder if you're interested in grabbing another one. So I'm going to read through these real quick, but like I said, there's more information on the sheet if you're interested. So the first requirement was that the robot shall stay within the budget that we were allocated. The second was that the robot shall be able to support its own weight while stationary. It also needs to be able to walk, power itself without outside assistance, be controlled autonomously, fit within the dimensions of the 2017 RoboGames that I mentioned earlier. We'd also like to design it with the intent to compete in the 2017 RoboGames and ideally win the 2017 RoboGames. Next, we wanted the Hexapod to be aesthetically pleasing, be able to interface with the manipulator when it is connected to it, be made of readily available tools and materials, be easy to maintain, be constructed using environmentally friendly materials and processes, be able to adapt on different surfaces, and finally, the Hexapod shall be able to be water and heat resistant. Now we're going to look at the design process and methodology we used for this project. The overview of the design project was that we took a weighted objectives chart in order to organize the requirements that you have in front of you from most important to least important. Next, we used a morphological chart to list out the sub-functions the robot needed to accomplish, as well as the solutions that could be used to accomplish those functions. Next, we picked 3 design paths through the morphological chart. So this is combinations of solutions in order to create an entire design solution, also known as design paths. The first one was a subsystem optimized path, and the other 3 were chosen by team members. Finally, we used a decision matrix in order to rank those potential solutions in order to determine which one had the highest utility and thus the best solution. Some terms that I'm going to use on the next couple of pages are weight. The weight is the value that is assigned to a requirement based on how it stacks up against the other requirements. So it is used to determine how important that requirement is compared to the others. Next, the score is a value that is assigned to a solution based on how well it accomplishes a requirement as determined by the subteam that it is relevant to. Finally, the utility is just the weight times the score, and we use that to get an average number in order to normalize and figure out which path is the most efficient. Now we're going to look at the weighted objectives chart. Again, the weighted objectives chart, we take the requirements that the robot needs to be able to accomplish, we list them out, and then we look at which ones are more important than the others. Here we have the weighted objectives chart. Take a minute to go over some examples on this. Along the top, you can see that the cost received a 1 as compared to all the other categories. This indicates that it is more important than all of the other requirements, thus making it the highest ranked requirement. Next, you can see that, for example, the dimensions of the robot as compared to the autonomy of the robot received a 0. That's because we determined that the dimensions of the robot were less important than the autonomy of the robot. On the next slide, we have the weighted objectives results. The score is simply the number of 1s versus 0s that a particular requirement got. Next, the weight is just 16 through 1 in chronological order. And finally, the percent is the weight that a particular requirement got divided by the total weight available. Now we're going to look at the morphological design chart. Again, for the morphological design chart, we list out the subfunctions the robot needs to be able to accomplish, solutions that could be used to accomplish those functions, as well as sub-solutions underneath each of the solutions. In an ideal world, we would go through and evaluate each and every single combination of solutions in the design path in order to determine which one had the highest utility. But for the purposes of this activity, we're only going to look at 3. Here we have the morphological design chart as it relates to the mechanical subsystem. You can see here that the functions that the mechanical subsystem needed to address were the structure of the hexapod, the actuation of the shoulder in both the horizontal and vertical direction, as well as the actuation of the elbow. For the structure of the hexapod, you can see that the mechanical subsystem looked at aluminum, 3D printing, and carbon fiber as their potential solutions, whereas under aluminum they looked at 3 different alloys. This is similar for all of the other categories. Next, we have the morphological design chart for electrical. You can see here the electrical team looked at the power as in the battery for the hexapod, 3 different types of sensors, those being stability and orientation, as well as lake fault detection and collision avoidance. And finally, they looked at the microcontroller the robot might use. Next, we have the morphological design chart as it relates to software. Software looked at the motion planning the hexapod would use, as well as the stability, orientation, and lake fault detection control algorithms the hexapod would use to accomplish its goals. Now we're going to look at the design selection. Again, we picked 3 design paths through the morphological design chart. Those 3 paths, the first one was a locally optimized path. The second 2 were chosen by the group. Here we have the overall morphological design chart that we looked on the last page. Now we're going to look at path 1. The design path 1, as I mentioned, was chosen by the sub-teams based on information that they used solely inside of their groups. The issue with this is it could result in an infeasible system. An infeasible system is when there are components of the robot that don't work well or at all together, and thus would not be a feasible path. Now we're going to look at the local optimization that the structure team did, the mechanical team did in order to determine which structure component they were going to choose as their locally optimized decision. You can see on this slide the weights directly pulled from the weighted objectives chart, as well as the requirements that were applicable to the structure of the robot, which were cost, tensile strength, durability, weight, the aesthetic appeal of that particular material, as well as the manufacturing speed, and if it was RoHS compliant. Again, for structure, they looked at aluminum, 3D printing material, and carbon fiber. You can see here that after the scores that were assigned to each one of the materials, aluminum received the highest score, with 3.8. On the next slide, we'll see how the design path got filled out. From the last slide, if you remember, the structure team picked aluminum. You can see that aluminum was selected, and then 6061, and so forth down the design process. Here we have a decision matrix that we use to evaluate the utility of a particular path. The way a decision matrix works is the requirements are listed out on the side with both their number and their description, as well as the weight, again, taken from the weighted objectives chart. Next, we have the score that a particular subteam assigned to the particular part of the solution based on how well it assessed that requirement for each of the 3 teams. You can see that for mechanical on line 4, They did not address that because the autonomy of the robot is not affected by any of their decisions. You can see here that the path 1 received an overall average utility of 0.732. Now we have an example of the work that a subteam would have done in order to determine the scoring that you saw on the last page. You can see here that the mechanical subsystem was addressing specification 1.1.1, which is that the robot could not exceed the mechanical budget that was assigned to them. You can see that if the potential solution they were looking at was much under budget, it received a 5, whereas if it was much over budget, it received a 0. This is a similar process that all the other teams went through in order to determine what score they were going to give to a particular solution based on how well it met the requirements. Now we're going to look at design paths 2 and 3. Again, design paths 2 and 3 were selected by group members based on background knowledge that they had. And the intent with this was to find a solution that was feasible and did not have any incompatibilities. Here we have the design path selection number 2. Some interesting differences to point out here is that the mechanical subsystem decided to switch to 3D printing material due to some background knowledge the team had in 3D printing. Next, we have the decision matrix for path 2. Again, you can see the overall average utility came out to 0.7145. Here we have the design path 3 selection. You can see the mechanical team went back to aluminum. However, an interesting point that I want to point out is that the software team switched from interrupt-driven control to polling-driven control. This is in order to allow the electrical team to use an integrated IMU instead of a non-integrated IMU due to incompatibilities that would arise from that combination. Here we have the decision matrix for path number 3. You can see the average utility of 0.736. Here we have the utility evaluation for all 3 paths. You can see on this table that the first and third path got very similar utilities, but as I mentioned before, the first path was actually an infeasible system. So that made path 3 our clear choice moving forward with our project. Up next, we have Mariah Sampson, who's going to talk about the mechanical design thus far on the robot as it relates to the path 3 that I just spoke about. Thank you very much.
Thank you, Evan. So for the mechanical subsystem, we developed a CATIA model in order to perform some simulations and analysis. Shown here, we have the full CAD model as well as a closer angle of the leg. So we decided to mount the servos at the shoulder joint. This reduces the inertial forces the shoulder or the horizontal shoulder joint experiences while the leg is moving back and forth, compared to as if the servo was mounted out at the shoulder or at the elbow joint. To control the elbow joint, we have some linkage. And then we have different components. We have a foot, a lower leg, linkage, upper leg, and then the body as a whole where the arm will be mounted once we integrate the 2 different systems. So we performed some finite element analysis on each of the structural components in order to ensure they won't fail without actually building and then testing the robot. So we applied a force of 40 newtons in the middle of the body plate. This is in accordance with specification 2.1.1. As you can see, the maximum stress this element experiences is 5.19 megapascals, and the maximum displacement is 0.0255 millimeters. These are minimal values and well within the range that we feel is safe for this robot. So next we perform the finite element analysis on the upper leg by applying a 42 Newton force and then a negative 42 Newton force at 45 degrees to estimate the vertical and horizontal inertial forces. As you can see in the equation, it's with an acceleration of about 3 meters per second and estimating the total weight of the robot to be 10 kilograms, which is above the actual weight that we found. We achieved 42 newtons. The maximum stress this element experienced was 35.8 megapascals, and the maximum displacement was 0.218 millimeters. Again, these are well within our range of what we feel is safe. Next, we performed the same analysis on the lower leg of the robot. The maximum stress this element experiences 29.1 megapascals. The maximum displacement is 0.5445 millimeters. again, this is 0.5 millimeter maybe, well within what we would feel acceptable while this robot is in motion. And we do not believe these elements will fail. Next, we applied a negative 40 Newton force on the foot in accordance with specification 2.1.1. The maximum force this experienced was 29.2 megapascals. The maximum displacement is 0.0031 millimeters. And then in order to make sure the linkage won't fail either, we applied the same force, 40 newtons in the negative z direction. Maximum stress this element experienced was 15.6 megapascals. The maximum displacement was 0.573 millimeters. Next, we applied a moment on the body plate where the manipulator would be attached, 15.9 newton meters about the y-axis of rotation of the bracket. This is in accordance with their specification 10.1.1. The maximum stress this experienced was 83.7 megapascals. So, and the maximum displacement is 0.089 millimeters. We compared both, or the stress this experienced with the bearing yield strength instead of the tensile yield strength, because when the arm is applying a moment, it will be bearing down on the plate instead of having a tensile failure. So this is well within our range we deem acceptable. So in summary, we have that none of our elements failed with the loading we applied using the finite element analysis, and our specifications 2.1.1 and 10.1.1 were met. In order to make sure we selected servos that would meet our specification 8.1.1 and 8.1.2, we performed a kinematic simulation with the leg. So the leg follows this path, and it repeats this path once every second. This is in accordance with how fast we would need to move in order to win the competition or finish the length of 3 meters in 7.75 seconds. So we get a graph from this. We have the angular velocity plots. As you can see, the maximum angular velocity any of the servos experiences with this simulation is just over 35 RPM. So comparing that to our servos that we chose, we are well within the no load range. Of course, this would be slower once we add weight and test more, and so we would have to ensure that these servos would move as fast as we want once we once we manufacture a prototype and are able to test it with the servos. If not, we'll have to adjust that to increase the speed or maybe increase the torque. All right, next David Olson will present on the electrical subsystem design.
Thank you, Brian. So first, I'm going to take you through some of the components we're using to power our system, and I'll show you overall schematic. First, we're going to talk about the battery. Our battery choice will be using 4 of the Grid 6 lithium-ion batteries. This holds a charge voltage of 25.2 volts and a nominal voltage of 21.6. It's able to draw 10 amps continuous with a 15 amp peak. It has a typical capacity of 3,450 milliamp hours and a total energy of 64.5 watt hours. And this is also lower weight than the traditional lithium polymer or LiPo battery. Next, for our power system calculations, to ensure that this battery would meet our needs, originally we were planning for a 7.4 volt system. However, with our new choice, this is a 21.6 and it does meet our specification, supplying plenty of voltage. For the power, we do reach the capacity. We'll be able to run our robot for roughly half an hour, which meets the specifications for 2.2.2, 3.2.1, and 8.2.1. The amount of current we're able to draw within these 4 batteries wired in parallel will be a maximum of 60 amps at a peak current. This is not ideal. This is not something we plan on running at all the time. However, it is possible and within the limit of our battery choice. Finally, our capacity. Between 4 of these batteries, we will have a 13,800 milliamp hour capacity, again enabling us to run for that half an hour, meeting specifications 4.2.1, 7.2.1, and 8.2.3. Next, our servo choice. We're using 6 of the MX64AT servos, as mentioned before, by the mechanical subsystem. These reach a torque of 6 Newton meters, which meets our specifications for 2.2.1. These have a 12 volt input and a 4 amp stall current. Next, we'll be using 12 of the MX28AT servos. These have a torque of 2.5 Newton meters, still meeting our specifications with that 12 volt input and only a stall current of 2 amps. We'll be using some voltage regulators using buck converters to step down the voltage from our battery to our servo motors. Our 12-volt regulator 1 will specifically be used for our servo motors. These will be able to take a range between 14 and 30 volts to read both our charge voltage and our nominal voltage of our battery and output 12 volts with an output current of 5 amps possible. We will also be using inline fuse protection to protect our motors because these are very expensive motors on the order of $300. So we definitely want to keep these from burning out. We definitely don't want to reach that stall current. Also, it might be important, we're not sure to what degree yet, but we'll do some further testing in the future to determine how low a ripple voltage we will need to maintain consistent behavior of our servo motors. Our 12-volt regulator 2 will be powering our microcontroller, which I'll be getting to in just a moment. Has an input of 14 to 30 volts and the same output of 12 volts, however, only has an output current of 2 amps, which meets the draw of our ERAU Neo microcontroller. Also, we'll be having one 5-volt regulator taking the same range of voltage inputs and outputting 5 volts. We'll have an output current of 1 amp, which we'll get to in a moment why it's there. So next, now here, looking to our schematic, you'll see that we have 6 of these 12-volt regulators, which will be powering our servo motor load. Each load is 3 motors in parallel, which will be daisy trained accordingly. And this will be one regulator will handle each of those loads. Our 12-volt regulator 2, as I mentioned before, will be controlling our ERAU Neo microcontroller. And there will also be a LiDAR system, which will be powered via USB. There's also a 5-volt regulator for what's called a buffer chip, and I'll be getting to the purpose of that later in the presentation. So to get into our microcontroller, we chose the ERAU Neo. It has Wi-Fi and Bluetooth capabilities, which are useful for debugging for the software team. What's unique about this is that it contains 2 different chips. There's a ARM Cortex M4 and an A9 core. It has a main processing chip, and it has a secondary chip, which is compatible with the Arduino IDE. This way, the software team can communicate with the peripherals via Arduino, which removes a lot of headache versus doing it all through simply C++. This board has an integrated IMU, which will be used for navigation and orientation. It has 1 gigabyte of RAM, again Arduino compatible, and the overall inverse kinematics will be programmed in C++ through the main chip. For leg fault detection, this is to determine whether or not our leg is actually on the ground. We'll be using a series of what are called force sensing resistors. You see that circular pad there. When a force is applied, it changes the resistance. When we drop a voltage across that, we're able to use that data feeding into the ADC, or the analog digital converter, of the ERAU Neo to determine whether or not our leg is loaded. This is independent of fluctuations in power and is readily available. Resolution is only limited by the ADC. The reason we went with this choice is, again, that we can discriminate between whether we have an electrical issue, a software issue, or a mechanical issue to determine whether or not our foot hit the ground. Next, for mapping, we'll be using a LiDAR module. These have high resolution, and a lot of the processing actually occurs on the LiDAR module rather than on our board, which will save us more time for the inverse kinematic calculations. A LiDAR module is already available to us on campus, which will help our budget a lot, being that this module is over $1,000. And this, again, this will be powered via the ERAU Neo via USB. Next, to go over our buffer circuit, the servo motors that we're using are not driven through BWM or pulse width modulation, and rather it's a variation of UART. Typically, UART uses 2 lines of communication to send data back and forth. However, with this, there's only 1 line. And what the buffer chip does, it basically controls whether or not the ERAU Neo is talking to our servo motor, or if our servo motor is talking to the ERAU Neo. And it controls who's talking to who, and it's made of tri-state buffers, essentially. This way, it's applied through TTL logic, is why it takes at 5 volts. Next, looking at our data schematic, this is how all the data will be transmitted. The ERAU Neo will be the hub of communication. We have the LiDAR, which is again powered with the USB. Our force sensing resistors will be receiving a 5-volt input. A voltage will be dropped across that, changing resistance, and then fed into the analog digital converter. And the buffer circuit will be in between all the servos, controlling all the communication within. Next, for our PCB, or printed circuit board mounting locations, we'll have a 12-volt regulator for our servo motors. At the back of each servo bracket, our 5-volt regulator will be positioned a little bit more from the front, and our ERAU Neo will be located directly in the center. And it's directly in the center for that IMU, so that way we have proper data for the orientation and heading of our Hexapod. Up next, Magnus Bergen will be talking about the software system design.
Thank you, David. So, as mentioned previously, the primary goal of the Hexapod for the software system is to control the robot during the 2017 RoboGames Walker challenge. This has This is going to be done using a kinematic controller that will be running on board the Hexapods, the ERAU-Neo, the microcontroller mentioned previously. This satisfies software specification 5.3.4. To your right here, we have the main flowchart for this mode of operation. I'll be going into detail on it shortly. Before that, however, I'll want to mention that the coordinate system that we're using for this hexapod is different from the more standard ones that are used in, say, aviation. For us, our y-axis points directly to the front of the hexapod, and therefore roll is measured around the y-axis. Similarly, x points to the right of the robot, and therefore pitch is measured around that. Normally in aviation, those are different. However, we chose this system as it makes the inverse kinematics models for each leg easier. So to begin on the main software flowchart, this is to reiterate for the robot when it's working during the 2017 RoboGames Walker Challenge. The hexapod will first start, it will initialize its graphical user interface and start recording data for debugging purposes especially. It will then initialize the inertial measurement unit and start taking readings. It will lastly go into a full stance where it places all 6 of its legs on the ground for greater stability before it begins. It will then proceed to start holding the inertial measurement unit and it check that the orientation error of the hexapod, the difference between its orientation, where it's facing, and where it wants to be facing. It will check that that error is less than 15 degrees. If it is greater than 15 degrees, the hexapod will then turn to face the correct orientation and then proceed. The hexapod will then next hold the inertial measurement unit once more, this time ensuring that neither the pitch nor the roll of the hexapod is greater than 15 degrees. This would make sure that the hexapod will not be falling over to the left, to the right, the front, or the back. If any of these angles are greater than 15 degrees, the hexapod will once more ensure that it's on a proper full stance on the ground and level itself for stability before proceeding. It will then go to the gait controller, which selects the x, y, and z coordinates that the feet of the hexapod will need to move through in order to propel it forwards. These x, y, and z coordinates will then be fed into the analytic inverse kinematics module of the software code. This takes those coordinates as input and then will create as output the joint space coordinates, the angles that the various servo motors need to move through in order to accomplish this motion. The hexapod will then move for a set distance and check if it has reached its goal, its destination or not. If it has, it will hold in place for safety. If it has not, it will start the process over again and loop. This system, this flowchart makes use of one interrupt, interrupt service routine, ISR. This checks that the the force being transmitted through any of the legs of the hexapod using those force sensing resistors mentioned earlier is not greater than 40% of the total weight of the hexapod. If it detects that that the force is greater than this 40%, this indicates that at least one of the legs of the hexapod that it depends on for stability is not in proper contact with the ground. And this would be dangerous for the hexapod, it might fall over. This will then cause the hexapod to go into a full stance, place all 6 legs on the ground, stop walking, level itself, and ensure that all is good before proceeding. This is done via an interrupt, as that allows it to be done at a higher level of priority versus the rest of the software code mentioned previously, as it's so important to the stability and therefore safety of our expensive hexapod and any humans who might be near it. We wanted to do this at a high level for stability and safety. Next, the other mode of operation consists of whether the hexapod is walking and detects that the manipulator, the tail system from the previous presentation, is attached. This means the hexapod will be operating in a second mode of operation where it communicates with the tail using parallel asynchronous communication between the control systems of the two robots. This satisfies software specification 2.3.1 as well as 2.3.2. In the communication between these two, the hexapod will send its position as well as the data from its inertial measurement unit. It will also send a step counter, which is used for navigation. In return, the hexapod will receive the position of the manipulator, and more importantly, data for the center of mass of the manipulator. This is critical as that affects the balance of the hexapod, and we don't want both robots falling over and possibly damaging themselves or anyone standing nearby. Lastly, the hexapod will also receive commands from the manipulator. For example, walk, stop, or turn to a new correct heading. Here's the flowchart for this mode of operation for the hexapod with a manipulator attached. As usual, the hexapod will initialize its inertial measurement unit and then go to a full stance. However, this time it will also send next that inertial measurement unit information to the manipulator. It will then wait in place until the manipulator will send it the desired orientation for the hexapod to face. When this data is received, the hexapod will turn to face that direction and then proceed through, as mentioned previously, the gait controller and the inverse kinematics, and then movement. Now, however, it will also increment its step counter, as mentioned previously, and then send that data to the manipulator. This allows for navigation in terms of where the hexapod has been and where it is now. as previously, the hexapod will then, of course, check whether the robot as a whole system has accomplished its current goal. If so, hold in place. If not, loop through the process once more. This flowchart makes use of two interrupts this time. On the left here, we have the position interrupt service routine. This ensures that the hexapod will always have the most up-to-date information on the position of the manipulator. As the manipulator encountered center mount on the hexapod, certain positions that the manipulator may need to take in order for it to accomplish its goal could possibly clash with the legs of the hexapod as they move. Therefore, the hexapod will need to know where the manipulator is to avoid any damage to the other parts of the robot. On the right, we have the center of mass interrupt service routine. Similarly, this ensures that the hexapod will always have the most up-to-date information on the current center of mass of the manipulator, as that is the one, as previously mentioned, very critical to the stability of the system as a whole. We will be doing next semester creating a dynamic controller for the hexapod. This is done via tackling the dynamic model of the hexapod, taking into account the number of their complex variables. This would allow us to use a closed-loop control algorithm to control the hexapod in motion. This has many benefits over the simpler kinematic controller. It allows for better control of the center of stability of the robot as a whole by accounting for the velocities and the accelerations of the various servo motors on the system. This also allows for better compensation for external forces, gravity or the friction between the hexapod's legs and the ground. We have not yet implemented this dynamic controller because the additional math essentially for it is somewhat complex, and we are so currently focused on getting an operational model that we may do testing on. However, we will be working on a dynamic controller next semester. Next, Stephen Rudrick will be covering the prototype work that we have thus far accomplished at software.
Thank you, Dennis. As far as letting the software subsystem gets their feet wet this semester, we were supplied a prototype hexapod by Dr. Gentilini, which had a very similar leg design to our hexapod design. This prototype used a Robotic OpenCM 904 microcontroller and was programmed in the Robotic IDE, and also used very similar Dynamixel AX12A and AX18A servos. Here's a forward kinematic model of the prototype hexapod leg. This starts at the body frame, which is at the center of mass of the hexapod, and extends to the end effector frame, which is at the foot of each leg for the hexapod. And it also demonstrates the three joints of actuation and their respective joint configurations, Q1, Q2, and Q3. For the results of the forward kinematics, the top equation gives the position of each end effector in X, Y, and Z with respect to the body frame, and the bottom equation gives the rotational matrix describing the orientation of each foot of the hexapod with respect to the body frame. These forward kinematic equations were then utilized to find the inverse kinematics, which would give the joint configurations for a desired end effector location, which met specification 5.3.2. This is important because we know where we want the foot to go in order to walk. We just need to find the configuration or angles of each joint to do so. Here's the equation for the configuration or angle of joint 3, and the equations used to find the configuration or angle of joint 2. As just demonstrated, the inverse kinematics had a lot of trig functions and were therefore very computationally intensive. And the Robotic MCU had insufficient memory and processing power to do those inverse kinematics on the board. Therefore, those inverse kinematics were offloaded to MATLAB externally, and then the results were implemented into the MCU. The prototype used a tripod gate controller, which meant that 3 legs were moving at a time. This increased the stability of the robot, which met specification 8.3.1. As seen on the diagram, the 3 legs will move in motion, and then the next set of legs will also move in motion. This cycle repeats cyclically for the hexapod to walk. The diagram on the left shows the foot motion relative to the hexapod center of mass. The foot starts off by lifting up, moving forward, moving down, and moving in reverse. It's important to note that when the leg is moving backwards, it is stationary relative to the ground, but moving relative to the hexapod center of mass. The dots for the left show the iterations in the inverse kinematics, to which the goal position of each foot would head to. This did have some limitations as it caused some inconsistencies and discontinuities in the trajectory of the servos. And on the right is a video demonstration of the hexapod walking. The prototype hexapod was also implemented to rotate. This was done by assuming that the feet would move in a circle and solving for where the foot is currently on that circle, then using some trigonometry to find the desired foot location where the foot would travel next. Then running the inverse kinematics and then implementing a similar gate controller. And the video on the right is another demonstration of the hexapod moving, rotating. Further implementation for the software of the hexapod would involve optimization. This will make sure that the code runs as efficiently as possible in order to have the hexapod walk as fast as it can, as well as orientation correction while walking. These two are very important implementations so that the hexapod can walk as fast as possible in order to compete in the 2017 RoboGames. We'll also be implementing stabilization and leg fault detection as described earlier in order to make sure that the safety of the hardware and servos are maintained, as well as integrating the manipulator and so communicate and complete various tasks together. We'll also be setting up a graphical user interface to help debugging the robot, as well as letting different software applications communicate, and then implementing a LiDAR for obstacle detection and avoidance. Now I'll hand it off to Sarah to talk about the summary of results.
Thank you, Stephen. All right, to begin, we're going to go over the mechanical subsystem mass budget. What the mass budget is a breakdown of the mass of all of the components that are comprising the mechanical subsystem. So you'll see in the first column is a description of the component itself, followed by the specific product that the mechanical system is going to use, the quantity of that product that'll be on the completed hexapod, the unit mass of that component, and then the total mass. This results in a total mass for the mechanical subsystem of just over 5.7 kilograms. This process was then repeated again for the electrical subsystem, and they resulted with a mass of 0.8917 kilograms. Together, these two masses were combined to create the overall mass at this point in time of the hexapod, which is just over 6.6 kilograms. This is aligned with specification 2.1 and proves that we're not over mass at this point in time. Next, we're going to address the unmet requirements. At this point in time, the only requirement we are not meeting is requirement 16, which is heat resistant. This is primarily due to two reasons. One being the high cost associated with implementing a heat-resistant hexapod, as well as it being our lowest priority in regards to all of our specifications. The other specific specification that is not met is 4.1.2, which is the mass of the leg itself. Here we have our Gantt chart, which is outlining our major milestones and activities for next semester. Most of this is in regards to fabrication of the hexapod, as well as testing and programming in preparation for the 2017 RoboGames Walker Challenge, and then additionally preparing for the critical design review at the end of next spring. So in summary, we've gone over who is on our team, the problem statement that was issued to us, our solution in terms of the requirements and specifications that we came up with to meet this problem statement, the design process we took to come up with our specific design, the design thus far in terms of the mechanical, electrical, and software design, as well as addressing our unmet requirements. And now I'm going to hand it back over to Evan.
Thanks, Sarah. Once again, my name is Evan Klein. I'd like to take a brief moment to thank Dr. Gentilini individually for helping us through this project, as far as helping us outline the design process we would use, as well as helping us determine which requirements and specifications we'd use. I'd also like to take a brief moment to thank Dr. Richard Mangum, or Professor Richard Mangum, for helping us review our documents and prepare us for this presentation, as well as Dr. Ann Bocher, Miss Ginger McGowan, Dr. Ron Madler for his support in the College of Engineering, Mr. Ernest Stokesbury for his support helping us make the parts for the robot, Dr. Brian Davis, Dr. Stefan Bruder, Professor Dennis Kodemer, as well as Mr. Jim Weber. Now I'm going to take approximately 15 minutes for questions. The way the question section is going to work, I'll hear your question, I'll try to repeat it back to you, make sure I fully understand it, and then if appropriate, I will direct it towards the appropriate sub-team to respond. Thank you very much for coming, everyone.
go to slide 61. So some of these are comments that you probably heard in the last one, but just to reiterate, that's not really a schematic, that's more of a block diagram, connectivity diagram. So if we're looking at a schematic, you probably want to go a little lower level than that. Some other questions on powering batteries, lithium-ion batteries. They're connected in powering, connecting parallel series.
So the lithium-ion batteries, to reiterate your question, we're going to connect them in a certain order in order to make sure that we're able to accomplish the tasks that the robot needs to be able to accomplish. And for that, I'm going to direct it to David over.
So we are wiring the batteries in parallel. So that will pretty much allow us to draw more current. We expect to probably be drawing between 20, 30, maybe 40 amps. Certainly not 60 at the peak current. That's really a drastic case. And I also know that you brought up with the other group making sure that the voltages are exactly the same so we're not drawing current in between batteries. That is an issue we have not discussed yet, but it's something we'll definitely take into consideration for the next semester to ensure the safety of our Hexapod.
Okay, so that was one of my concerns. And the other one is related to your regulators. What type of regulators are those that you're using?
We'll be using buck converters.
You're using buck converters as well. And have you looked at power dissipation? I saw voltage and current on there, but I did not see power calculations.
So what we're doing to do our voltage regulation, we're taking a little bit more of a workaround before we even get to the heat. Specifically with the regulators for the servos, which will be dissipating the most amount of heat. What we need to make sure is that there's a low enough amount of voltage ripple. It's been noticed by the software subsystem as well as Dr. Gentilini that the behavior of the motor changes as the supply voltage changes the characteristics of the torque, which will mess up the dynamic model. So first we need to determine whether or not we can use a COTS system or a commercial off-the-shelf, which is already with a built-in heatsink and that issue is taken care of. Or if we have to go the PCB route where we mill it, populate it, and test it, then we'll need to consider going to heat sinks and whatnot to make sure that we do not go over temperature.
And then another question, I go, what kind of surface are you planning on using? This isn't for me.
Yeah. So, as mentioned in one of our specifications, the robot is designed to be able to accommodate 3 different surfaces. And in our requirements document, I believe those are listed as the surface at the RoboGames, which is a concrete floor with the obstacles that are described by the definitions of the RoboGames, as well as carpeted floors, because those are common around campus. And then we were also talking about other surfaces as far as polished tiles might be another issue. And so for that, we wanted 3 different styles of feet, maybe a pointed foot as well as something covered in rubber for traction, and then maybe a blunt foot, depending on if the surface is fractured or something.
Okay, yeah, that was my question, because your toes look pretty plain. I was wondering if you were on the gym floor or something like that. And how much have you been talking with your other team about mass of their tail and how that's going to affect your center of gravity and so forth?
Yeah. So the mass of the other team has been, they've given us a maximum weight and we've designed around that. So our specification states that the combined robot will not weigh more than 10 kilograms, and currently our robot's at just around 7. And so that accounts for their maximum mass that they told us of 2.5.
Now, that affects your sensing if you have more than 40% of your mass on any foot. You said that's a fault, is that right?
Correct.
Okay, and so that's assuming that you have like 33% on each of the ones that are down, right? And now when you have a tail on the one back, might that put more weight on your rear feet that you might have to think about?
So that's a software question I'd be happy to defer to Magnus to answer that more thoroughly.
That is, currently hasn't been accounted for, however, that is a adjustable feature that we have programmed into the code that we could adjust the weight for different features depending on what we convert to. So that's, to go address your question more directly, you could account for the different, like have different limits that they would check for safety.
Thank you very much for your questions.
I had the same question about the 40% in the walking, with the arm, whether or not that would throw off balance. And I was just going to ask you, in terms of safety and competition, essentially if you hit that and stand up in the competition, you've lost. So you can leave that check in there that says if we think we might be going off balance, stop. Is this something you thought about?
Yeah, so to clarify your question, basically during competition we'll not have the manipulator attached, as they'll be competing in another competition at the same RoboGames, and they're not critical to the competition that we're trying to compete in. So that particular concern is not significantly being addressed at this moment. However, there was a question in our practice presentation yesterday if the robot experienced when it was climbing over objects, it experienced a certain angle of incline that would cause it to enter its full stance condition. And based on the size of the obstacles and based on the steps at the end of the competition, we don't believe that's going to be a problem. But as Agnes mentioned, we have the ability to edit the code in order to accommodate that evidence.
The other question is, you showed the video of it rotating.
Correct.
I have to ask, with the six-leg design, is that necessary? Or do you have to move forward and rotate, or can you walk in different directions?
Yes, we can program it to walk in different directions.
It might be faster.
Thank you very much for your comment.
I have a couple questions. So if you go to slide 53, this kind of follows up on something you just mentioning. You mentioned the 60 amp limit, and you wouldn't be doing that all the time. Do you have any conditions where it would require the 60 amps? Do you know of anything currently that you're asking it to do that it would be drawing 60?
So to reiterate your question, the motors on the robot are going to be able to potentially draw a maximum of 60 amps. He's asking if there's a potential for any potential circumstances in which that would happen. So for that, I'm going to defer to David as well.
So in that case, if you were to reach that, that would mean that all the motors are in stall, which is not a good thing, because that means we're getting close to burning out those $300 motors. If that were to happen, that would probably most likely if we're climbing up an incline. That means that the amount of weights distributed such that there's more loads in those motors. Luckily, between the Walker challenge and basically what we're planning, we're really not planning to take any hard inclines that would cause for stall current. Rather, what our goal was with these batteries is that we put a ceiling on the current way higher than we know we're going to reach, so that way we don't limit ourselves in the future. If we want to go faster in our competition or something, we know we can reach the current draw, and that will not be a limiting factor. Does that answer your question?
Yes.
Additionally, as David mentioned during his slides, there will be individual fuses on each of the motors that are going to act as a thermal fuse in case there is a problem, and those will auto reset. Any further questions?
Sorry, I have a couple more
Absolutely.
questions. On 67?
We actually have a lot of backup slides. If you have any specific questions about specific details, we have more information on those.
You do a check of 15 degrees for roll and pitch, and it was mentioned that this is to avoid tipping over. I'm assuming the tip over angle is not 15, but have you calculated what you anticipate the tip over angle to be?
So the tip over angle that we came up with for the robot was 15 degrees, and I'm going to defer that to Magnus to speak more.
As mentioned in, I believe, our specifications document, part of the programming is designed that it's very reprogrammable. We avoid the use of hard-coded variables. 15 here is more of an example one. We have that will be changed most likely as testing proceeds next semester. So 15 is an example used here. We can adjust it very easily if needed.
So you haven't calculated what it would be for the vehicle yet? Okay. Let's see. On 89, I can understand the heat resistant requirement being a lower priority because you are not planning on moving it through fire for your current demonstrations. Are there any ramifications of not meeting the specification 4.1.2 that your leg mass is not less than the 0.15 kilograms?
So the leg mass of not less than 0.15 kilograms was something that came about very recently, and we've been trying to address that, and I'm going to defer to Kristen Sandegger to speak more on that.
Okay. Originally, we were planning to go with lower torqued motors. For our minimum torque is 2.5. We were going to go just a little above the minimum we needed, and then have a mass of less for the leg. We were going to go with 3D printed or something like that weighs less. And then we were able to buy more expensive motors that have a much higher torque, and because of that we were able to go with aluminum for our structure, which is heavier, but it's also has a much higher stress.
So would it be safe to say that the specification has changed because your motor selection has changed, or is it still you need to be less than that 0.5, or you would like to be less than that 0.5?
I'm going to I will have to defer to our CAD lead for that.
Okay. So your question is if specification, if not meeting specification 4.1.2 is, are we going to change that specification or are we going to try and meet it?
So it sounded from her answer that you're not concerned about not meeting this because you picked better motors that could handle a bigger torque requirement and so on. So this is not a concern. Is that correct?
Yes, and we're also, as you saw in the finite element analysis slides, the legs are over-engineered to a certain degree, so we can almost certainly take mass out of the legs to meet this requirement again. In a detailed design, we can further refine the design to reduce the weight.
Okay, thank you. That was awesome.
Thank you. Yes.
So just as a clarification, are all the requirements outlined on this sheet from the robotics challenge, or are these requirements you've set?
These are requirements that we've set. However, there's a couple of requirements in there that are specific to the robotics challenge,
Okay.
like you mentioned.
So, for instance, the budget, is that yours between URI and COE, or is that for the competition?
The budget that we have for the robot, our class pursued URI funding, and with that URI funding and the funding that was that is allocated to detailed classes or frequent classes, we divided that up between the two teams evenly, and that's where that budget came from.
So getting the LiDAR donated, is there a budget restriction for the competition, and will the donated LiDAR influence that, or?
So the LiDAR in specific is not required for the competition. We're only going to be trying to go forward. It will be using the orientation control to maintain the forward direction, so it might not even be on the robot at that time. However, there is not a budget requirement for the RoboGames, and so we don't need to address that. However, we don't. If you're interested, we have the actual budget slides. For example, the servos that we're buying, we're buying them in a large quantity because both our group and the tail group are using the same servos, and so we're getting a discount on that. And then we're also part of an educational institution, so we're getting another discount about that. And so our actual cost is much higher than what our actual deliverable cost is.
Okay.
Here you can see the total price versus the adjusted price, almost a difference of a couple $1,000.
Okay, cool.
Does that answer your question?
Yeah, I would, just I guess as a recommendation for detail, if you were going, differentiate what the requirements for the Robo Challenge are and the requirements you set. So, because, yeah, I got a little confused as to what was what.
Thank you.
Can you go to that slide back, please? I think part of the confusion also is that none of those statements are requirements. Those are all objectives and constraints. Okay. What differentiates requirements typically from objectives and constraints is there's a numerical value associated with the requirement.
So, to address your question, you're saying that requirements.
I haven't asked the question.
Oh, okay, well,
Yeah.
sorry.
I'm just making a statement. So typically, you have these objectives, and you also have some constraints. Objectives establish what are the goals of the project. Why are we here? Right? Constraints tell us what we have to work with. Right? And then, based on the constraints that are given, you start going one by one on your objectives, and you start determining what do we need to do, what needs to happen in order to satisfy these objectives, working with the constraints that are given. And that's why there's always a numerical value associated, because that becomes important, especially when you're validating the requirement. Have we met this requirement? And if all your requirements have been generated correctly, then by definition, your objective should be satisfied.
Okay. I'd like to thank you very much for your comment. Would you be interested in explaining the methodology, if I explain the methodology we used for this? So as you can see here, this is our requirement 1. And as described by the process that Dr. Gentilini helped us make, and then we worked with him in order to figure out how exactly we wanted to use it, we used a requirement in terms of what you're calling an objective. And so with that, a specification then becomes the, I forget the word you used.
Requirement.
Yeah, exactly. And so it's just a little bit of a different design process.
Okay, so it's just terminology.
Correct. And so as you can see here, specifications have hard numbers in them, whereas requirements do not. And I believe that's just a difference in terminology that we're using versus the way you'd like to be using. But
No.
thank you very much.
Gentilini ones.
Thank you very much for your comment.
Yeah, and just, same thing I mentioned to the other team, you got a slide 35. Are there any specifications associated with these values? You made the claim, that this is adequate for our needs. Okay, based on what? Is there a hard value that you're designing for? It should be less than this, it should be greater than that. So be careful when you make claims.
Yeah, so if you don't mind, I'm going to defer that question to Mariah Sampson, my mechanical lead, and she's going to talk about exactly what specifications that particular slide met. Because it did, if you could go back to that slide. As you can see on the third bullet point, it's got M spec 2.1, but I'll let Mariah speak more to that.
So, yeah, so we're wanting to make sure that the structural elements did not fail when our load specified. I believe it is in requirement or specification 2.1.1. And so we don't have a specific requirement or specification related to stress, but we kind of observing the values and just with our knowledge, like the displacement is on all of the elements is less than 1 millimeter. So it's teeny tiny.
According to what?
Well,
Relative to what?
we aren't,
I'm
compared
being
to,
argumentative.
yes.
Do you understand what I'm asking?
So,
Yeah.
yes. But since we're not flying this, we don't have to worry about that millimeter of difference. It's on the ground, and the force that we have applied is much higher than we would expect the robot itself to experience, especially in such a concentrated form. So 40 newtons would be on each of the elements. So about 4 kilograms, and then times gravity, so 40 newtons. We would have to further test to make sure that none of them fail once we have it built, but at this time we're not worried about it based on the analysis we've performed. So we have to further test to ensure that it doesn't fail, but with our preliminary design as it is, we aren't worried about it.
And what if it does fail? What's the contingency?
We would redesign whatever element failed in order to create a higher, just a higher factor of safety to make sure that it wouldn't, and maybe redesign the leg, which would probably be the most likely element to fail itself.
So you plan to do your testing early in the semester?
Yes.
Okay.
So the CAD model we have up there might be modified a little bit before we change, or before we actually build. But as is, that should be approximately what our design will look like. And so we plan on building within the first few weeks of the semester. And then testing and making sure everything doesn't fail. And if it does, we would redesign and retest.
Okay, thank you.
Thank you very much for your comment, though. The difference between the fact that we've specified a amount of load it needs to be able to take, but then haven't specified what the results should be is a very good comment. Thank you. Yeah.
This is more just out of curiosity. You do have a big team, a lot of hands on deck, and you evenly split out between mechanical, electrical, software. Do you have a breakdown of labor hours for each group to see if having equal groups is the right way to pursue this? Or like maybe, you found your software team putting in many more hours. I don't know if you have that or not.
I understand. So as you mentioned, we do have a very large team, but we've got a lot of manpower and a lot of very talented people that are working on it. And this semester, we believe that we've split up the groups in a very effective and even way in order to make sure that the work is evenly distributed. I know for a fact that the software team did a lot of work in the universe kinematics, and they're very good, and it's come out great. However, next semester, we are going to reconvene and try to see if we need to redistribute the manpower throughout the team in order to address it, because there is going to be less need as far as mechanical and electrical goes and more need towards software.
Yeah. So you don't necessarily have a breakdown of labor hours?
We do not.
Okay, might be helpful as well. I know, for instance, like the AE groups go into crazy detail, which I don't think is necessary, but I think it would be pretty cool for people to see that distribution.
Thank you. Any further questions? Probably have time for about one more. Dr. Gentilini.
So, where is this project going to fail?
Where's the project going to fail?
Yeah. What is the biggest spot in your design?
So the current hurdles that we're most worried about right now is just failing. On the Gantt chart, we have a decent amount of time over break for servo testing before the complete servo order goes in. For the tail team, we've already ordered servos, and with that, we've got a couple of extra that are exactly the same as the servos we're going to be using. So we're going to be performing testing on those over break to make sure that they're going to be able to meet the needs that we have, because that is the most expensive part of our robot, and thus once the servos are here, the rest of the hexapods are really going to have to conform to what those servos are capable of. And so I would say that's probably our biggest worry right now. But we're working to address that as quickly as possible. All right, if there's no further questions, I'd like to thank you all for coming. It was a pleasure.